All right, I think it's time to get started. Yes. So hello everyone, and welcome to another Arena online seminar. My name is Panos Gastis, and I'm going to be the host in the online seminars this year. Before we jump to the presentation, I would just like to remind you to mute your microphones so we can reduce the background noises. If you have any questions during the presentation, you can unmute yourself and ask it, or you can type it in the chat and I will make sure that will get addressed and we'll transfer it to the speaker. Today, I'm pleased to introduce you to Dr. Jaspreet Randhawa. He is a postdoctoral research associate in University of Notre Dame in the United States. Jaspreet specializes in the field of experimental nuclear physics, and his research focuses on the measurement of nuclear reactions of astrophysical interest using active targets. So Jaspreet, when you're ready, you can start.
Okay. Thanks, Panos. So I hope you can hear me.
Yep, we can hear you very well.
Thank you. Okay, so topic for today is constraining the key input to X-ray burst models, and I will specifically emphasize on the role of active targets because that's what I'm using as a tool to investigate the different nuclear reactions which are important for X-ray bursts. Here's the outline of my talk. I'll start with the introduction to X-ray bursts, a brief introduction, and then I'll talk about our two recent works. One is the fate of material accreted onto neutron star and what is the role of nuclear spallation, and then the measurement of 22 magnesium alpha P, which is another recent work. I'll talk about the experimental details and implications for X-ray bursts. And then briefly towards the end, I'll talk about the upcoming experiments with the, at least one experiment with the cryogenic solid hydrogen target, which is a 59 copper P alpha. Again, another experiment for the X-ray burst and the commissioning of our new TPC at Notre Dame and possible future measurements with this type of detector. Okay, so the basic quest is that what happens to the material that gets accreted onto the neutron star. So as the material is accreted onto neutron star, in the atmospheres, it can undergo spallation or nuclear spallation, which is a proton-induced spallation. And this is our new work that I will talk about, how it can alter the initial abundances or initial composition, which is used for in the X-ray burst models. And then the material settles down into deeper layers where temperature and densities are conducive enough to start hydrogen and helium burning, which leads to type 1 X-ray bursts. The gravity is such that the ashes, instead of becoming part of interstellar medium, instead of being ejected, they get further buried deeper into the neutron star. And that leads to these ashes, they leads to a superburst, and they can undergo electron capture and then settle down in lattice, and they leads to the picnonuclear reactions. So the processes, nuclear processes which are happening here, they dictates what happens in the core and in the crust, outer crust, and then the processes which are in the outer crust, for example, the heat generated from these reactions, they impact the X-ray burst. So that is our understanding. So what I'm going to talk about today is the spallation and reactions and how they can alter the initial composition. And then I will talk about the type 1 X-ray burst and the reactions we have been working or trying to constrain, which directly impact the X-ray burst light curves. So the type 1 X-ray bursts are the thermonuclear explosions on the surface of accreting neutron star when the material is secreted onto neutron star from its companion. Once the conditions are conducive for the different type of nuclear reactions, these bursts, they are powered by the sequence of nuclear reaction, for example, hot cyano cycle. And once the triple alpha reaction ignites, it triggers the burst. Then the flow from hot cyano cycles break out, and that leads to alpha P and RP process. And all these different nuclear processes, they shape the different part of X-ray burst live curves. Now, the main uncertainty that as a nuclear physicist we can constrain is that the nuclear reactions well, I'm mostly focused on nuclear reactions, but there are other things also. And also these nuclear inputs, they directly impact the modeling of light curves and the burst ashes that are predicted, which as we see that they play a crucial role in the layers which are further deeper. So let me first talk about what happens to the material as it is accreted and before it settles down for and the temperature and densities are enough for the type 1 X-ray burst. So this is the idea by the Bilstein, where they presented that as the material is accreted onto the neutron star, due to the Coulomb interaction with the electrons, the elements gets stopped at some point, and the column density, electron column density required to stop the particles depend upon their atomic mass and atomic number. So different elements, they get stopped and thermalizes at different heights, let's say. And then, so heavier is the element, more shallower depths it will get stopped. And the protons and helium, they get stopped at very larger depths. So that means where these heavier particles are stopped, these protons, incoming protons, still have almost their infall energy, and they can induce the spallation reactions. And that, so what Bilstein they looked at in the paper was that they looked at the isolated destruction of carbon, nitrogen, and oxygen, and predicted that there is very tiny fraction of these elements which survive. So we will see in a minute that how these CNO abundances affect the burst and further processes. But they also explicitly mentioned in the paper that a full cascading production and destruction mechanism needs to be studied. So that is the root of our paper, which was already mentioned in their work. So the idea is that what we want to see is that whether if we take a full reaction network, instead of just looking at the destruction of carbon, nitrogen, and oxygen, since there are heavier elements also, so destruction of heavier elements will replenish the carbon, nitrogen, and oxygen, and that's what we are studying in. We studied and we are interested in. So we use the NukeNet tools codes, the single zone model. So we use the full reaction network, and reaction network included the spallation reactions and the beta decay. And we studied the cascading process and tried to see how this cascading process affects the abundances of carbon, nitrogen, and oxygen, or CNO in general, or how it impacts the CNO metallicity. So this is these are our results that we have from the cascading processes for different mass accretion rates. The red color crosses that you see, they are the solar abundances, and what we have in the blue dots, different color dots, is the abundances that we get after the spallation, before it gets settled down to the layers where it's conducive to burn the hydrogen and helium. So what we see is that above the boron, almost all the elements, they are destroyed to subsolar values. And the important thing is that this method also provides the mass accretion rate dependent initial abundance for the X-ray burst. So what I mean by replenishment is that now if you look at the time integrated reaction flow here, since we consider the full cascading process, if I ignore everything above the carbon and I just look at the destruction of carbon, that means I'm ignoring all the flux that is coming, that is generating or that is constructing the carbon from the spallation of heavier elements. Here I've only shown a snapshot from neon to carbon. So you can see that there are many channels which are also producing the carbon. And if we only look at the isolated destructions, we will ignore that. And here is the carbon abundance with respect to solar as a function of mass accretion rate. This is the isolated destruction, and this is in the replenished model that we see, the cascading destruction model. And the final carbon abundance, the survival is much more higher. It's several orders of magnitude higher than the isolated destruction. So what it shows is that if we solely focus on the isolated destruction, we will underestimate the final carbon which will be present during the ignition. Okay, so what impact does it have on ignition conditions? Now, this is well known and has been studied before, that before the burst ignition, as the material is being accreted, and during this accretion accumulation process, the hydrogen is burned via CNO cycles. Okay, now there is what amount of hydrogen will survive at the time of ignition. That depends on the competition between the mass accretion rate and the burning via the CNO cycle, rate of burning via the CNO cycles. But the rate of burning, hydrogen burning via CNO cycles, that depends on the CNO metallicity and hence the presence of carbon, nitrogen, and oxygen. So if you see here, I use the code settled by Andrew Cumming to see how much hydrogen survived at the time of ignition as a function of mass accretion rate. The black lines is if we start with the solar CNO metallicity, and as the mass accretion rate decreases, it cannot compete with the hydrogen rate, hydrogen burning through the CNO cycles. So the hydrogen is depleted at the time of ignition. But if the abundance of the CNO cycle is lower, the abundance of CNOs or CNO metallicity is lower, the rate of hydrogen burning through CNO cycles will be lower, and what you are left is with much more hydrogen at the time of ignitions. So what is important here is that we still see a difference, but if we take the isolated destruction model or our replenished model, which is the blue dots here, which could play an important role. What impact it has on the burst ashes? So on the burst ashes, we tried to look at we took one of the abundances that we have here, the abundance distribution, and use it as an initial abundance in MESA, and try to see what impact it has on the burst ashes. So if the metallicity is lower, the one observation is that abundance distribution is shifted to higher mass region. This gray histogram, field histogram you see here, that is for the solar, and the line histogram, they are for the different values of CNO metallicity, or the overall metallicity, let's say, which is mostly CNOs. So this is again linked to what we see previously, that as we lower the CNO, that leads to reduced hydrogen burning during the accretion or the accumulation time. Hence, more hydrogen is survived and hydrogen-rich conditions during the burst ignition. This leads to extended hydrogen burning. This has been observed before, and this is understood before. But what is important here is that the resulting burst ashes, they can differ by a factor of 2 or even more if we take the different metallicity. One here is the isolated destruction model, which was previously assumed, and the replenishment model. So there is already a factor of 2 or more in the abundances from these two predictions of initial compositions we have. Okay, this was for before what happens before the material gets accumulated, like during the accumulation, the spallation, and how it impacts the X-ray burst. Now, I will move to the nuclear physics input and impact on the X-ray burst live curves. So the sensitivity of the nuclear reaction rate, sensitivity of the light curves and burst ashes to different nuclear reaction rates have been studied very thoroughly in many studies. There is one of the study by Richard Seibert, and here what it shows is the impact of different P alpha and alpha P reaction rates on the light curves, on the X-ray burst light curves. On the right side is the impact of one of the varying the one of the reaction rate, 15 oxygen, alpha gamma up and down, and the impact on the burst ashes. So this means that the uncertainty in the nuclear reactions can impact the X-ray bursts in two ways. One is that few reactions directly impact the X-ray burst light curves, and few of them cannot impact the burst ashes, which, as we have seen before, that sets the stage for processes which are further deeper in the deeper layers. So, but why it is important to model better the X-ray burst life curves? We see that, okay, the ashes, they play an important role in the deeper processes. So the reason is that the modeling of the X-ray burst light curves, it is important for the model observation comparison. So if you see from the left side here, this is the light curves which were observed for this source, which is known as also the clockbuster, because it's well behaved, or let's say textbook example of X-ray burst. And then on the right side is the comparison of the light curves with, on the right side is the light curves, but it's the impact of different reaction rate variation on this light curve. So if you see here that we want to compare from flux to luminosity, and that's where the redshift and distance to the source comes into picture. And if we can constrain our nuclear reactions better, or let's say the uncertainty in the nuclear reactions better, we can better predict the redshift and distances. Or if the distances are known, then redshift, or the surface gravitational redshift, which can tell us more about the compactness or mass radius of the neutron star, underlying neutron star. So since we're talking about the X-ray burst model observation comparison, one of the reaction rate which has been shown to impact the X-ray burst light curves is 22 magnesium alpha P. This is from one of the studies which shows the impact on X-ray burst light curves. These are the light curves and by Zach Meisel using MESA, and here he has shown impact of 22 magnesium alpha P variation by a factor of 10 up and down, and you can see that how it changes as compared to the observations of this for the same data source that we were discussing before. Now the question is that, okay, here it shows the variation by a factor of 10 up and down here and here, but in reality, how much is uncertainty in 22 magnesium alpha P? So the current So the current status of 22 magnesium alpha P is that it comes from the indirect measurement of the resonances in 26 silicon. So this was done by 28 silicon PT to explore these resonances, which can play an important role in the total cross section and the total reaction rate. But if you see here in this region, which is important for the X-ray burst light curves, if you see the scale here, it's huge, and it differs from order of magnitudes different from the statistical model based Hauser-Feshbach based calculations. And especially above the 1 gigakelvin temperatures, it really falls down, or not fall down, it really diverges from the theoretical predictions, which was attributed to lack of resonances above 10 MeV in 20 silicon. So there's a need of direct measurement, and that's what we did with the active target and NSCL, and that's what I'm going to talk about. So the question is that why active, or even to say that why the innovative target designs? This is slide mostly for the people who are not the nuclear physicists, but maybe they can still try to understand. So the main motive is that we want to study this. We have to study these reactions with radioactive beams. The challenge is that these are very low intensity beams, as it's very challenging to produce these different beams as we move away from stability, both on proton-rich side and neutron-rich side. So the problem with the conventional targets is that you lose the luminosity, and also other effects are that even sometimes the reaction products have so much low energy that they will not even come out of target. And if you try to make target thicker, which is, okay, this is a little bit exaggerated picture to demonstrate. For example, if your target is thick, and these are, I show two scattered particles scattered at same angle, but they're being deposited in the different segments, and you will record them as a different angles. So you end up, and then also this is the beam energy after the target. This is the target thickness for some beam here in a pure solid hydrogen target and in the polyethylene foils. And the beam loses so much energy if you try to make this target thicker, and you have to make that energy pin much larger for the direction of interest. So the solution is that we need to have the innovative target designs. Even though I'm mostly going to focus on ATTPC or the active target time projection chambers, here are a few designs which I feel that I can share. One is the solid hydrogen target. The thin film is made on the silver foil, and this is the chimene, which can produce a thin film of hydrogen. I have not seen the physics results with this yet. If any of you have come across, I will be very interested to see if they have really tested this target and it's effective. So please let me know. And then there are other gas targets like the JINA-CEE gas jet target, which can produce the jet of the gas, and then also in very small reaction vertex. When you reconstruct your reaction, it's very advantageous. And other detectors are also like MINOS, that where you have the liquid hydrogen, and then you track the particles and you outside the detector, and then you trace back the vertex. So what I'm going to focus on is the active target time projection chamber at NaCl, which is what we use to measure this reaction rate or reaction cross section. So the advantage of the active targets are that it allows the 3D imaging of nuclear reactions and nuclear decays. The idea behind it is that your target material, which is the gas with which the detector is filled, it also acts as the detector medium. So as the beam goes in and there's a reaction or there is a scattering, any nuclear particle, they will ionize the gas. And as the gas is ionized, this is under the, so there's a field cage which makes a uniform field, and electrons drift under that field. And once they're very close to the pad plane, just 100 micron above the pad plane, there is a mesh. And this is the region where the amplification takes place. So the advantage behind this is that you still regain the position from where this electron came, X and Y position, and timing will give you the third position, the Z position, or the position along the beam. Also here, this is the micromegas here, and on top of that is a thick gas electron multipliers, which has been used before, which also allowed the use of pure gases as a target instead of using some quenched gas along with them. So the ATTPC at NaCl, it used to be sitting inside the 2 Tesla magnetic field inside a solenoid, which is shown here. So that means the trajectories, instead of being the straight lines here, what we will see is the helical trajectories, and then we have to identify and analyze the reason it is inside the solenoid is that from these helical trajectories, one can get the B-raw values, and that leads to the identification of these different type of particles that we can have. Now it will be sitting in even more stronger solenoid in the area 6 hall. So because this solenoid is already dead. Okay, so we done 22 magnesium alpha P with the 22 magnesium T-accelerated beam at 5 MeV per nucleon, around 800 to 900 particles per second. And we filled the detector with helium CO2. At that time, we were not prepared to use the pure gases, so that's why helium CO2 was used. Now we can use the pure helium also if we have to perform this now. This is the Bragg curve for the beam. So beam completely stops inside the detector as the beam comes from this side. It completely stops inside the detector. So that means you can get the full excitation function in the single beam energy in one go. So these are different type of particles or events which we see. For example, this is some kind of fusion evaporation on carbon and oxygen, where you can see the multi-particles, and this is alpha 2p and then on alpha also. What we are interested is in this type of events, which is alpha p22 magnesium alpha p. So one way to do was that if we look at the kinematics, the only protons are the backscattered from the kinematics. So what we tried to see is that we looked at the events which are single events and they are backscattered. So here is there are many ways to differentiate between single events and multiple events. For example, here is 3D hit pattern, and you can project that hit pattern as the angles. You can get the angle for these two tracks, and then you can identify if it's a single event or it's a multi-particle event. And you can further do the Randsack analysis. You can fit this part with Randsack and project arc length versus the Z or the beam vertex or the reaction vertex. So this slope also provides you an angle. This is an independent way from here. For example, this is the scattering at below 90 degrees in lab. This is scattering above 90 degrees in lab. And this is our events of interest. So this is how we identified the alphas or the alpha P channel. And then the reaction vertex, as I said, that this is the projection of z-axis around the arc length. You can get the reaction vertex from here or through this way. If you put the distance from the z vertex, then that's what you will see, and they both agree with each other within 1 or 2 millimeters. So what we finally have is that this is the reaction vertex position as a function of lab angle. As I said, that we only looked at the protons which were backscattered. So the blue triangles is our data, and this is the simulated simulation, which also includes the detector acceptance, the red ones. As you see that we do not see the protons all the way up to 160 degrees. So the reason was that if I plot the number of pads hit per event, this is the versus the angle. You see that in the data there is a sharp cutoff at how many number of pads were hit per event. And if I use that in the simulation, then I agree with the simulation. So the
I think we lost Jaspreet.
reason was that
Jaspreet,
the trigger threshold, which was yeah, you cannot hear me.
I think there is a problem with the connection.
Okay, can you hear me now?
Yes.
Okay, sorry, but so
no,
okay,
that's fine.
So what I was saying was that so our trigger was that a multiplicity trigger, that only if this certain number of pads are hit for a given track or for a given event, then only record that event. And that trigger was set a little bit higher. That's why we saw this acceptance only up to 130 degrees in the lab frame. Okay, so this is the results I have. The blue dotted line is dashed line is the non-smoker from the non-smoker code, and this is the data points that we get. This is the weighted energy for each energy bin we have. The points are black dots are shown as the weighted energy. And what we see here is that if we divide the non-smoker rate by 8 or 8 times lower the non-smoker rate, that can somewhat explain our data. But what we did is that we optimize the Thales parameters to fit our data here, and then use that extrapolation to get the reaction rate at the lower temperatures or at lower energy. So this is the comparison that we had. This is the from Matic et al., which was the indirect measurement. At the lower temperatures, we do agree with their measurement, but then as they said that above certain temperature or above certain energy, they lack the data about 10 MeV states in silicon, the compound nucleus. So that's why you see that their energy dependence is different than what we see here. Now, the impact this new reaction rate has is that if you see that this is the for the baseline, which is the black line here, and then this is the red is our work here. So what we have is that we have a reduced 22 magnesium alpha P compared to the statistical model based calculations. So what means is that it will feed more to 22 magnesium P gamma and 23 aluminium P gamma, which will make 23 aluminium P gamma even more. I hope there will be chance to measure this reaction with the SECAR in future. And because this is going to be even more important reaction now with this study. And from this redshift versus distance, if we try to fit to the observations, what we inferred is that there is a less compact neutron stars, because if you see here, this is shifted in the time, which means that the redshift has changed. That leads to the less compact neutron star. Okay. Now the upcoming measurement that we will have. This is the 59 copper P alpha. This is another important reaction which can directly impact the X-ray burst light curves. Now the reason is that if the P alpha is stronger, this is actually the competition between P alpha and P gamma. If the P alpha is stronger, or if the P alpha is stronger, what it does is that it stops the flow and it cycles back to nickel. So that's why it's called copper nickel cycle, and that's why there's a sharp drop in the energy, and the light curves are very different. The similar process has been studied in the neutrino P process by Arcones, and they also said that it's a competition between P gamma and P alpha, which leads to copper nickel cycle. So that's why it's important to study this reaction cross section, the P alpha. So P gamma is also equally important, but I think that will also be another important reaction that SECAR might be trying to do in the future, which will be a very important reaction. So as a proof of concept, what we tried to do is that we took the 19 fluorine beam and we did P alpha reactions with a solid hydrogen target. So what we have is a very low. So what we have is a very low pressure ionization chamber before the target, and then we have this solid hydrogen target. This is a thin film that is so there's a silver foil, and then there's a diffuser that goes very close to silver foil, and the silver foil is cooled down to 4 degrees Kelvin, and then the hydrogen is sprayed onto it, and it sticks to the surface as a solid target. So then the lighter particles or the reaction products, they are stopped in detected in delta EE telescope, which is a silicon, and then there is a cesium iodide at the back of that. The unreacted beam and the heavier particles, they can go and be detected in other silicon array. So this is the delta E versus E from this larger telescope, silicon cesium iodide telescope, and this we were able to separate out the alphas from the protons. So this setup will be used to study the 59 copper P alpha, and I'm hopeful that we will be able to do it this December. Of course, I will not be able to join due to the COVID conditions, but hopefully they can still run this experiment. Now the final step I'm going to show is the commissioning of the new TPC, what we call the ND cube or Notre Dame cube, which we recently commissioned. This is the 3D rendering of 3D ND cube. This is the high voltage feed through, and then this is the field cage. You can see here that this is the high voltage feed through touching the cathode. This is a cathode plate, and then there's a field cage, and then at the bottom of it is we have a high granularity pad plane. We have around 100,000 pad planes in the area of 26 centimeter by 16 centimeter. And this is one of the example scattering events that we see from the lithium plus helium scattering we commissioned with lithium beam and the helium CO2 gas. And we also commissioned with the lithium beam on argon as a P10 gas. And we have a lithium beam around 1200 particles per second. So what we see here is again that this is the track of the beam particle, and you see the drag curve for the beam particle. And this is an example fusion event. This is how we identify the fusion events. So it stops much earlier. If the fusion happens, it stops much earlier and in the detector, and the total charge is deposited is much higher. That's a signature of our fusion. This is currently very preliminary analysis I did during the commissioning run for this fusion cross sections. This is our data points for 1 hour data, and this is the pace for calculations I got. So this will also provide an opportunity to study the fusion cross sections with the neutron-rich isotopes for the pignonuclear reactions, which we will try to do with this detector. So this is all I have to say, and I would like to say thanks to your attention and thanks to all the collaborators. Special thanks to Wolfgang Mittig from NSCL, Henrik, and then Zach Meisel from Ohio, and Panos himself. He was at NSCL before. Sorry, Panos, I didn't put the Las Alamos yet. So, and thanks to all the other collaborators.
Thank you very much, Jaspreet. That was a very nice presentation. Thank you. Are there any questions for Jaspreet? Please do not forget to unmute yourself before you speak. Nope. I guess I can start.
Yeah, sure.
So Jaspreet, about these spallation reactions that you talked at the beginning, did you do any sensitivity to see the impact of the cross-sectional sensitivities in those spallation reactions?
No, I didn't.
Experimental data in that region?
No, I didn't do any sensitivity study. So what instead we are doing right now is that because the cross sections are known on the stable targets, for example, iron or oxygen or carbon, the spallation cross sections. But what we are trying to do is that use that data to predict the cross sections if on the unstable targets using the machine learning techniques. So let's see what we predict, and if we can reproduce that in future, if people who are really doing the spallation reaction cross sections.
And so what are the proton energies for those spallation reactions? So
that is the mostly the infall beam energy. So infall energy is around 200 MeV, I would say.
200 MeV. Any other questions?
Maybe people want to go for lunch, so it's okay. Yeah. Or maybe already had the lunch.
So sorry, can you hear me?
Yes, we can hear you.
Maybe I have a question. It's Franco Galtarossa from AGC Lab in Orsay, France. And concerning the experiment you were showing of the magnesium 22 alpha P reaction with ATTPC,
yeah,
I would like to ask you concerning the possible background that you have in this kind of measurements. You were showing the fact that you were selecting backward angles to avoid all the alpha reaction, essentially. But do you have also problems coming from, for example, from inelastic scattering of the magnesium on the gas quencher? So in your case is CO2, if I'm not wrong.
Yes.
So if you have a proton decay of the magnesium, do you have issues then in detecting?
So the maximum background estimation that we had is 3% from carbon and oxygen, the protons that you will see from carbon and so I would say that this is the fusion evaporation reaction on the carbon and oxygen, from where you can see the protons, right?
Yes.
So the estimation is that around 3 to 4% maximum.
Okay, so it's very small. Okay, thank you very much.
Any other questions?
I guess I went too fast. Okay.
I have one more technical question, Jaspreet. Yeah. So when you saw this solid target, this hydrogen solid target, what is the thickness of this silver foil that you use for cooling down the hydrogen?
That is, right now it's 4 micron.
4 micron.
So I can go back. Yeah. So right now, yeah, this is 4 micron. But the good thing is that you can get the experimental contribution from that foil. That you, for example, in every experiment we take the data with hydrogen target, and of course 12 hours or even more data without hydrogen target, just beam on foil. That will give you an estimate on what kind of background you can have from that foil, if there is any.
Nice. So one last round for questions. Someone, yep.
Sorry. I have a question about the center of mass energy that you can get with the magnesium 22 alpha P reaction. Because I know in neon 22 plus alpha there's various resonance structures, and the cross section can vary quite significantly over some orders of magnitude due to the resonance structures. Do you see anything similar in the magnesium 22, or is it all kind of smoother?
It is kind of smoother because my energy bins are much larger, and that is because of the limited statistics I have. So it's the averaged yield, let's say, for that.
Okay, thanks.
Okay, I guess we don't have other questions. So let's thank again Jaspreet for his presentation, and hope to see you all again in the next seminar, which is in about 2 weeks from now.
Thanks.
We thank you very much, Jaspreet. So have a nice day or night, everyone.